record. There we go. And now I've got to share the notes. Oh, not this screen though. I'm so far off. I want it open here. So go back here. Sure. The correct spot. And what was that? Oh, that's just, why does addition work on 3? Oh, I just got rid of it. Ah! So addition worked on 3. Sorry, now I got to go back and share it again. Yeah, so essentially my addition rule tells me that I can go from P to P or Q whenever I want. Now that Q can be absolutely anything. So since we started with A, I can turn it into A or whatever the heck I want. And the whatever the heck I wanted was not B in this case. Because the person who was doing this proof knew where they were going with it, but they knew they were going to need a not B. So we could make this Q whatever the heck we wanted, and we just decided to make it the entire thing of not B. So you can add on, whatever you want, as long and ridiculous, as complicated as you need to. Addition just means you can tack on whatever you want.
Why was that step necessary, though, since the next one was modus ponens on 1 and 3? You never used 4, right?
Oh, because I wrote it wrong. 1 and 4. Sorry. You can't use modus ponens on 3. You needed 4. Sorry. Since modus ponens, we needed this entire thing to be able to use it. So yeah, sorry, that was my bad.
I have a question.
What?
So again with the modus ponens, the 1 and 4 is both of those numbers, as far as both of those are needed to make it use modus ponens, or?
Yeah, so modus ponens needs 2 separate things to use in it. So whenever you use modus ponens in a proof, you need to refer to 2 different lines, because you need 2 different kind of inputs, if you will, to actually use the rule. And the reason I could use it here is because essentially we were having the P was going to be equal to the A or not B thing. And then our Q was C. So that's kind of why we needed line 4, is we needed that entire kind of hypothesis, if you will, of that first statement to be able to use modus ponens.
Okay, I got you. Thank you.
Mm-hmm. If there was a not in there, it'd be modus tollens, right?
If there was a not in there, the not would have had to be on the C. So if you wanted tollens, you would have needed a not C. But that also gets you not P instead of Q. Oh, now I'm writing all over the place. That's not going to go over well. So yes, modus tollens is a kind of completely different thing that you need. You need a not something and then just an implication. Did that make sense? Should I write it out separately instead?
Yes.
A yes to making sense, or a yes to I should write it out separately?
Write it out separately.
Okay. So, whoops. Bring that back in a second. So let's bring back what I had already written, P, and then that gets you Q. So this is ponens. So say you wanted tollens. Well, tollens tells you not Q. P implies Q. Gets you not P. So say we wanted to try to bring this into the proof in the warm-up. So P here would still be equal to A or not B. And we still could make Q equal to C, but then what we would have needed in the warm-up is we would have needed not C. And if we had this, the thing that this would have given us, though, this would have given us not A or not B, which would have not been helpful at all for the warm-up, but that's what it technically would have given us. So they're 2 different rules, and they get you completely different pieces as well, because one of them essentially pulls out the hypothesis, the conclusion, if you will. Modus ponens essentially pulls out the conclusion, whereas modus tollens gets you a version of the hypothesis. So it's like depending on what piece of the implication you're trying to pull out, it's going to make a difference in what rule you're going to try to use. Does that make sense?
Yes.
Okay. Someone in here had a question? Yay! Any other questions? Okay, now on to the notes. That I gotta get back to now. Here we go. So, on Tuesday, sorry, I gotta, yep, no, I'm recording. I'm sorry, I just wanted to triple check that. So on Tuesday, we started 1.3, so we started talking about our predicates, which are our, for all and there exists. So we have the universal quantifier, which is the for all, and the existential quantifier, the there exists. And we went through all this jazz. So we're down to example 4. And remember, we also are now working with domains, which is what's telling us what we're allowed to plug into these kind of functions, if you will. So in the domain of non-zero integers, let I, x, y be the predicate, x over y is an integer. Translate the following into English, determine whether the statement is true or false, and explain why. Nope, I want to draw. All right, so the first thing is we're going to translate them into English. And the nice thing is it does you just kind of read it from left to right and write it as you're reading it. So the first piece we have here is for all y. Now, whenever you want to write down a variable, you should also specify the context that it's in. So we're going to say for all non-zero integers y. So we kind of add in that context of the domain that we're working in. So for all non-zero integers y, there exists a non-zero integer x such that, and now we have to just write out what ixy means, and we're told that it means x over y is an integer. So again, it kind of just reads itself out. So the symbols from left to right, for all y, there exists an x. So for all non-zero integers y, there exists a non-zero integer x, I of xy. Now, is that true or false? Well, we got to think about the kind of order that we're working in. So for all non-zero integers y, that means I give you a y value, and I can give you whatever y value I want. There exists an integer x. So I tell you a y, you spit me back an x, and you just have to have one of them. But for every single y, you have to find me one. So for any y I give you, can you spit me back out an x such that x over y is an integer? Yes. This is true. For example, there's multiple examples you can give here, but for example, as our little explanation of why, for example, let x equal y. Then x over y equals y over y equals 1, which is an integer. So we've just found no matter what y value I give you, you can literally just spit the same number back to me and it's an integer. You could also spit me any multiple of that number that I give you and you'll be fine as well. Does that make sense? Okay. What about essentially if we switch those quantifiers in the front? So now we've got, maybe I should keep the entire problem in there. So now we've got there exists some non-zero integer x such that for all non-zero integers y, x over y is an integer. So unlike last time essentially once you see a for all, it's kind of like, ooh, I should be careful with my phrasing. Let me explain this one first. So there exists an integer x means that there's one and it has to hold for the rest of the thing that I say. So if the there exists kind of happens first, you got to fix it, and then it's fixed for whatever comes afterwards. Okay, that's why in the last one it was kind of like I throw you whatever y I want, but then you fix an x that works. So here we have to fix an x. So I say, okay, x is going to be whatever x has to be. And then you start shooting y's at me, and my x has to work for every single y you give me. So this singular x has to work for every single y. So does there exist at least one integer that would work for every other y value such that x over y is an integer? No. That's never going to happen. This one's false. For example, let y be equal to 2x, because again, whatever x this is, let's say I imagine I have an x that's going to work, then y can be whatever I want. So let's say y equals 2x. Well then x over y is equal to x over 2x is equal to 1/2, which is not an integer. And of course, there's a bunch of other examples you could use as well, but we just need one of them to say it's false. Make sense? So here, the thing you really want to pull out is that it kind of matters the order. Whenever you have there exists an x, it's kind of fixed for everything that comes afterwards. But if you have a for all y, it can be whatever the heck you want. Questions, concerns before I move on? Chat. No, it will not. The quiz will be like the warm-up, and that's it. So if you were okay on the warm-up, hopefully maybe the proof one's a little iffy, but the only thing that's going to be on the quiz is the proof thing and the contrapositive converse thing we did in the warm-up. All right, so moving on. What? Why? Just scroll like a normal computer. Thank you. So we also want to be able to negate these quantifiers. Yay. So we want to be able to say not for all p of x or not there exists p of x. So essentially what happens, well, let me just say their names first. So we have universal negation, and existential negation. Now, essentially what's happening is you're going to bring the negation inside the quantifier, and you're going to switch the quantifier. So you kind of just bring the not inside, and then the quantifier changes to the other one. Bring the not inside, and it changes to the other one in both cases. Now, instructions on homework and such are going to say something like simplify until no quantifier and no connective lies within the scope of a negation. Now, the other day we defined scope. The scope is just the thing that's in the parentheses after the quantifier. So essentially what's going to happen is if you have, not for all x, p of x, and that should be a bracket at the end, not a parenthesis. This is going to be bad because the not is still in the scope of a negation. And the other thing it's saying is it doesn't want you to have something like this, or even, now this last one is a bit trickier to kind of get away from, but all of these are essentially, if you have the not kind of outside of a scope of things, it's going to want you to push it through until you can't push it through any farther. And we're going to see that in an example in just a second. Is that? No, okay. So let's look at well, kind of an example. So in example 2 that we started on Thursday, it was the example where we were using if X has wings, then X can fly. And, we were talking about penguins that have wings but can't fly and all that jazz. So we were looking at the two statements. The one was for all of X, Q of X implies P of X. And the other one was there exists Q of X and not P of X. It actually turns out that the second is actually the negation of the first. And I want to show you why, which will also help you realize what I mean by negating these things and having to pull them in, because we're going to see how we're negating the first one and having to do a bunch of rules to get down to the second one, okay? Now, this is also going to deal with mostly the equivalence rules, but nope, mostly the equivalence rules. So these are still going to be used in our lives. So we're still going to want to remember them. Well, you'll have them, but use them. So let's see how that's going to work. So we are essentially saying that we want to negate for all X, P of X implies Q of X. Q of X implies P of X. Sorry. My bad. So we want to negate this. And we're going to kind of write this out as a proof. So this is just the given. So the first thing we're going to do is use that negation rule. So we're going to use our universal negation on 1. So we're going to bring the negation inside. Whoa, I've already screwed up. I was just doing the inside bit and then I was going to screw it up in a second. So you bring the negation inside and you switch the quantifier. Everything else stays the same. So you bring the negation inside, switch the quantifier. Now, again, this is where we don't want to leave that not outside of that implication, but we can't just push it through. We have no rule that says how to negate an implication. So we actually need to change this implication into an or statement. Yeah, an or statement using the implication rule. So we're going to use implication on 2. There exists in X stays the same. And then this implication is therefore going to become not Q of X or P of X. So that's using our implication rule. And now that I have an or statement, I do have a rule that tells me what happens when I bring the negation in. It's De Morgan's law. So we use De Morgan's on 3. And I know you could easily do 2 steps in one, but with proofs, you always got to do it out in painful, steps. So it's got to stay not. I've already screwed up. What is with me today? So you bring the not into both, and then the sign flips. That's what De Morgan tells you. And then our last step is the thing that you would probably be tempted to do all at once, is to take the double negation and just turn that into Q of X and not P of X. Double negation on 4. And this is exactly what we said we were going to get. But this is kind of what it means by don't let a negative lie outside of the scope of a quantifier or logical connective, is you have to bring it kind of all the way through, if you will. It's directly connected to a P of X or a Q of X. It's not in front of a thing involving a string of P of X's and Q of X's. Savvy? Time. Because of where we're at for time right now, I'm going to jump over to 1/4. I'm going to come back and do the rest of the examples, but they are examples that we've kind of already seen an example of, so they're just kind of repeating in a bit more detail. But I want to jump over to 1-4 specifically because your homework covers 1-3 and 1-4. So I don't want to leave today without you having anything from 1-4 to be able to take and do on your homework. You do have all of the tools you need from 1-3 already. We'll come back to these examples on Tuesday and catch them up before we keep going. But anyway, so I'm going to jump over to 1-4 that I need to pull up really quick. Oh, I already have them, but I just need to make it. But the start of 1-4 is mainly just lots of definitions, so it's nothing too super heavy. So 1-4 is logic in mathematics. So in this section, we're going to discuss math terminology and elementary number theory, which is super fun. Number theory is a lot of fun. Well, I think it's fun. You guys probably won't think it's fun, but I'm weird. So definitions. Now this one's funny because I'm about to define a definition. So the definition of definition. So a definition is a statement that stipulates the meaning of a new term, symbol, or object. In mathematics, a definition tells us exactly what we know about the term, and we should be careful not to assume anything else. If your definition doesn't say it's true and you're like kind of implying something else from it, that's not good. The only thing we know from a definition is exactly what it tells us and nothing more. So, a couple of mathematical definitions are: an integer n is even if n equals 2z for some integer z, for some integer z. For example, 12 can be proven to be even because 12 can be written as 2 times 6. So your 6 would be your z. We have a similar definition for odd. An integer is odd if it can be written as 2z plus 1 for some integer z. So for example, 13 can kind of be proven to be odd because it's 13 equals 2 times 6 plus 1. In your homework, some of them will say something like, show, I don't know the exact wording, but like show 2n plus 15 is odd. And it essentially sets it up like this, and it leaves you to fill in this box here. So what you need is something to put in there such that when you expand that out, you're going to get 2n plus 15. Well, if you think about it, you've got a plus 1 tacked on the end already. That's already there. So essentially, the thing you would need to build up to plus 15 is you'd need a 14, right? But since it's inside the scope, if you will, of that 2, to get 14 out of that, you would want it to actually be a 7, right? So your answer would be n plus 7, because if you expanded that out, it would turn into 2n plus 15. So that's kind of what your homework's getting at with those. It's kind of trying to force you to figure out what it could be such that when you expand it out, it does show that it is odd. Does that make sense? Another definition. I'm not sure if this one pops up in your homework or not, but just in case it does, because it's in the book. 2 lines are parallel if they have no points in common. Pretty sure we all have seen parallel in our lives. This one might be new to you, or at least defining it in such rigor. A non-zero integer m divides an integer n if n equals k times m for some integer k. So m divides n if you can have some integer that you can multiply m by to get n. A number that divides n is called a divisor of n. And also notation, I don't know why I haven't put this in yet. So notation, spelling. If m divides n, we're going to write that as, let me not get this backwards, m divides n. So it's just like this little line thing. Now you want to be very careful because a lot of people get this backwards in their head. I'm going to hold on a second because people are writing. Let people catch up. Sit and breathe. So, for example, 3 divides 12. For some reason, a lot of people expect the larger number to be on the left. It's not. Because this is saying that there is a number, there is an integer that I can multiply 3 by to get 12. You can multiply by 4. So it's saying that 3 divides 12 because there is a number that I can multiply by 3 to get 12. If m does not divide n, then we just put a little slash through the line to say it doesn't divide it. There does not exist a number such that m times that number equals n. Savvy? Okay. A prime is a natural number. My pen started freaking out. Natural. A natural number. So n is greater than 1. With no divisors other than n and 1. So prime numbers can only be divided evenly by themselves and 1. Prime numbers 3, 5, 7, 11, 13, 17, 23. I get a little sketchy after that. But essentially, those numbers, you can only divide them evenly by themselves and 1. They, except for 2 is also a a prime number. 2 is a prime number. It is the only even prime number that exists. Every other prime number is odd because every other even number is divisible by 2. So odd numbers are 99% of the time odd, but 2 is also a prime number because it's only divisible by 2 and by 1. Okay, definitions in math are logically equivalent to an if and only if statement, even though they're kind of usually only stated as ifs. So you can always go both ways. You know, so a definition, if two lines are parallel, if they have no points in common, but also if they have no points in common, then they're parallel. So they do go both ways, even though they're kind of logically written as an if statement. Yeah, we got time. The next set is a bunch of definitions. There we go. So, or maybe, no, just do it. So, sorry, there's no A in there. So, axioms are statements that are assumed without proof. These are sometimes also called postulates. Axioms are kind of fundamental statements about the objects they describe. We assume as few as possible because we want to make sure that the bulk of the things we're assuming to be true can be proven. But to be able to prove things, we do need to take kind of some things for granted, if you will. For example, now axioms, there's no like one set of axioms. If you go to a geometry class, there's one set of axioms. If you go to a number theory class, there's another set of axioms. If you go to an algebra class, there's another set of axioms. So it kind of depends on the context you're working in. and they kind of pull the axioms that they kind of need for that specific thing. But some examples of axioms would be, if n is a natural number, then so is n plus 1. Like if you have a natural number, also maybe people might not know what natural number is. Natural number is essentially any integer greater than 0. So 1, 2, 3, 4, 5, 6, 7, 8, blah, 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 blah. So it's kind of assumed to be true that if you have a natural number, if you go to the next one up, it's also a natural number. Like that's kind of something we take for granted. We don't really prove it. Some other ones, another example would be the fact that a plus b equals b plus a. We kind of take that for granted and without proof. One last one would be if you have that, a equals b. If you subtract the same thing from it, it should still be equal. That's another thing that's true, but we kind of accept without proof. So that's kind of what I mean by an axiom. And again, we try to take as little of those as possible and prove everything else from them. So, theorems are statements that follow logically from axioms and statements that have already been proven. So essentially you say something, you can prove it's true, it's a theorem now. We kind of have some things that are kind of below theorems, but we've got something else first. I'm getting ahead of myself. A proof, everyone's favorite thing, is a valid argument based on definitions, axioms, and other proven statements that demonstrate the truth of a statement. Essentially, you use axioms, things you've already proven, to prove something else. You can't take stuff that you haven't proven yet and use it in a proof. So the answer to that is quote unquote no. Especially ones like these. Do we ever get tested on definitions? But say the Lord, my words. The thing I kind of say is that, think about going back up for a second. We have this definition of divides. If I ask you a question about whether one number divides another and you don't know that definition, you're not going to be able to answer the question. So that's kind of how I view quote unquote testing definitions. I actually test the concept of it, but no, I'm never going to ask you what is the definition of a definition. What is the definition of theorem? I don't do that. But some of so these ones a little less, but like the ones above with using, even, odd, divides, those are like the definitions that you really want to make sure you know. So we use them, we just don't have to write them. Yeah, that's a good way to put it. Yeah. More definitions. Which one am I at? My numbers and my notes don't match the numbers on here. Proof. Okay, a claim is a statement that we intend to prove. So pretty much we're like, this is a true statement, I'll prove it later, kind of idea. And then a conjecture is a statement that is suspected to be true, but has yet to be proven. So it might actually turn out to be false, but like you really trust and believe that it's probably true, you just don't know how to prove it yet. Or you just haven't taken the time to prove it yet, and you're not sure how it would work. Okay. I'm going to get through this last, I'm just going to finish off this page. We could actually almost finish 1.4 right now if I rushed, but let's not rush. So we often have statements of the form for all x, p of x, right? Which we saw in the last section that we're still going to come back to in a little bit. And that the negation of that is there exists an x, p, not p of x. Both of these statements cannot be true. And I mean at the same time. You can have cases where one is true and then another case where the other one is true, but at the same time, they can't both be true. You can't have it true for all of them but then have one that it's not true for. So you can't have them both. So that is to say, if we want to prove our axioms conjectures, they were, what? No, sorry, no, they're not. Axioms are not conjectures because axioms are specifically taken to be true without proof, where conjectures are things that need to be proven. So axioms are kind of their own special kind of glorified position, if you will, of not needing a proof. But everything else that's not an axiom needs a proof. That was a good question. Anyway, where was I? If we wish to prove for all x p of x to be false, that means we only need to find one value that makes not p of x true. We need to find that there exists an x such that not p of x. Because then that statement would be true, and therefore the for all x p of x would be false. This value of x is called a counterexample. My pen is freaking out. So say we wanted to find a counterexample to the statement, every prime number greater than 3 is the sum of two prime numbers. So I want to find a counterexample. So first off, let me start listing off some of our prime numbers. We've got 2, 3, 5, 7, 11, 13, 17, 19, and I'm going to stop. Now, specifically here, we're stated greater than 3, so we kind of got to cut off those first two. And hopefully, this is going to fall out pretty quickly, so let's just kind of start and see when we can find one. So let's look at 5. Can you write that as a sum of any two prime numbers? Well, that's 3 plus 2, so that's not going to work. What about 19? And 5? I'm vastly confused for some reason.
Well, 19 5 equals 24.
Oh, but 24 isn't prime. We want to find a prime number that isn't a sum of primes. So here I have that 5 is a sum of two primes. So you think that 11 doesn't work? You're probably right. Let's see. What about 7? Well, 7 I could write as 5 plus 2. So that's not going to work. What about 11? Well, I'm looking and I'm looking and I'm like 7 plus 2, 7 plus 3, 7 plus... Doesn't look like it's going to work. But we should kind of prove that there's no way to write 11 in terms of two primes. We shouldn't just say, oh, I think it's true. We should show that it's actually not possible. So let's write all the ways we could find the sum of 11. There's not as many as you think. We could do 1 plus 11, 1 plus 10. Brain, what am I doing? 1 plus 10. We could do 2 plus 9. We could do 3 plus 8. 4 plus 7. 5 plus 6. And then they start repeating just in the opposite order, so just frickin' stop. Well, those aren't two primes. 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 Oh, I found it. 11 is a counterexample. Because it is a prime number that is not able to be written as the sum of two primes. That makes sense? Questions, concerns? $210. Yeah, we'll just call it. We only had a tiny bit more in 1-4, but I don't want to rush it. We'll come back to it on Tuesday. Like, really, that was all we had left. But anyway. So we'll go about taking our quiz now. So that means, let me unshare this. Let me get them off the screen. So I'm gonna stop the recording, stop the oh, it's recording on here. I forgot. I'm dumb.